Welcome to the mechanics of rest. The day leaves a residue of conversations. The tones remain more than the sentences. The small adjustments you made to keep things smooth. The unfinished replies still waiting somewhere in the mind. None of it needs to be held now. You can let that residue settle, as dust settles when a room grows still, while your shoulders loosen and your breathing finds its own slower rhythm. There is nothing to solve in this hour, only the sound of a calm account moving forward. If this steadiness is welcome, a subscribe and a like help these chronicles return each week. It is a small, quiet way to keep the door open for more nights like this. This is the story of a universe that has remained silent, and of the careful reasons that silence has been measured. It follows the listening more than the absence. You may let go now, and the telling will keep its own pace. Chapter 1: Los Alamos, Summer 1950. In the summer of 1950, Enrico Fermi left his office at Los Alamos for lunch. The air over the mesa held heat, and the laboratory buildings lay low against the sky. He walked with Emil Konopinski, Edward Teller, and Herbert York, colleagues accustomed to quick calculations between bites. Their conversation drifted as conversations do, from work to the newspapers. A recent series of reports about flying objects had caught public attention, and the topic surfaced easily. The group reached the dining hall and found a table. Talk turned from the sensational accounts to the underlying plausibility of visitors from other stars. Konopinski recalled a cartoon. Teller offered a remark about propulsion. York listened. Fermi listened as well, turning the discussion over in the manner that had become familiar to those around him. The subject was not new to physicists, but the newspaper context gave it a lighter edge. Layers gathered over time in a way that could be felt more than counted. Seasons pressed upon seasons, and the slow cooling of rock recorded each passage without haste. Continents drifted a little, then rested, then drifted again, and the record of that motion accumulated in strata. Stars above turned in their courses, and their light arrived after long journeys through clear space. The accumulation did not hurry, and it did not pause for any single moment. By the time the coffee cooled on the table at Los Alamos, the galaxy that contained the mesa had already lived for about 13.6 billion years. That duration allowed many generations of stars to form, to burn, and to seed the space between them with heavier elements. Fermi held that number in mind, not as an abstraction, but as a span that dwarfed any human project. If a civilization arose even a small fraction earlier than humanity, the head start would be measured in millions of years. The slow accumulation of time made such a head start seem ordinary rather than exceptional. Fermi carried a habit of rapid estimation, and he applied it without ceremony. He considered the time required for a technological species to expand at modest speeds, well below the speed of light. Even at a few percent of that speed, the crossing of the galactic disk would require tens of millions of years. Compared with billions of years of available time, that interval appeared brief. The reasoning did not depend on any exotic physics, only on persistence. At the table, Fermi did not lecture. He asked a short question that followed from the numbers already discussed, and he phrased it in the plain language he preferred. Those present later recalled slightly different wording, but the sense remained consistent. The question pointed to the gap between the time available for expansion and the lack of any clear evidence for it. It was not delivered as a challenge, and it did not seek an answer in that moment. He did not raise his voice, and he did not linger on the point. The conversation continued around him, touching on other topics before the meal ended. York later wrote that the remark was brief, almost tossed aside. The brevity was characteristic, and it allowed the idea to travel without the weight of argument. Conversation moved on, as conversations at Los Alamos often did, toward work waiting in the afternoon. The group left the table and returned to offices and blackboards. No notes were taken, and no formal record was made that day. The idea persisted because it fit easily into the mental toolkit of physicists trained to compare scales. A walk across open ground can illustrate the kind of distance involved. Steps accumulate without drama, and the horizon remains distant for a long while. The ground cools underfoot as the afternoon lengthens, and the pace stays even. There is no sudden arrival, only the steady addition of one stretch to another. The body learns the scale through repetition rather than through any single effort. Interstellar distances behave in a similar manner when considered at low fractions of light speed. A journey of a few light years requires years, and a crossing of the galaxy requires millions. The numbers are large in human terms, and they remain small against the age of the stars. Fermi's estimation rested on that comparison, not on any imagined breakthrough. The walk extended, became a measure rather than a barrier. Decades later, Michael Hart returned to the same comparison and set it down in a journal article in 1975. He treated the expansion time as a calculable quantity and compared it directly with the age of the galaxy. His conclusion followed the earlier lunch table logic, though expressed with formal references and figures. The paper gave the question a durable form in the literature. It also ensured that later discussions would begin from a shared set of numbers. There is a pattern worth noting in how a casual question becomes a research direction. The question itself does not change, but the context around it thickens with measurements and instruments. What began as a remark over lunch later supported observing programs and funding proposals. The transformation is quiet, and it proceeds without announcement. Los Alamos in 1950 provided a particular setting for such remarks. Physicists gathered there were accustomed to moving between abstract theory and practical engineering. Estimating orders of magnitude was part of daily work. Above the mesa, the night sky remained clear and reminded observers of the scale overhead. That environment did not create the question, but it made the question easy to ask. Absence, in this context, was not treated as mystery. It was treated as a datum that could be compared with expectation. If many civilizations had arisen early, some sign of their expansion might have accumulated. The lack of such a sign suggested that at least one step in the sequence was uncommon. The reasoning remained cautious, and it avoided conclusions beyond what the numbers allowed. The question remained. It waited for better telescopes and longer listening. Later accounts varied in small details, as memories do. Some placed the conversation outdoors, others at the table. The names of those present stayed consistent, and the core of the remark stayed consistent as well. Variations did not alter the underlying comparison of timescales. The story persisted because the numbers behind it were easy to reproduce. Human lifetimes tend to misread galactic time. A million years feels immense in daily life, and it shrinks when placed beside billions. Fermi's habit was to hold both scales at once without forcing them to match. That steadiness allowed the question to remain open rather than urgent. The summer lunch ended and the afternoon work resumed. No announcement followed, and no program was founded that day. The remark entered informal circulation among physicists, carried by retelling rather than by publication. It gathered weight slowly, as ideas often do when they fit available measurements. The afternoon light lingered over the mesa while the question, unanswered, stayed in the background. Chapter 2. Hart turns a question into numbers. Michael Hart returned to Fermi's lunch table remark in the early 1970s and treated it as a problem to be measured. He worked at the University of Illinois and at the time wrote about interstellar travel with the same steadiness he applied to other physical systems. The remark had circulated informally for 2 decades, and Hart decided to place it inside a formal argument. He did not add new speculation. He organized the existing scales into a single comparison. The work required patience more than invention. He set the galaxy's age at roughly 10 billion years for the purpose of the calculation. The disk had existed long enough for many generations of stars to form and disperse their material. Hart considered how long a civilization might need to cross the disk if it expanded at speeds that remained far below that of light. Even with conservative assumptions, the required time stayed short compared to the available time. The comparison turned a passing observation into a quantitative tension. A front can advance without hurry and still cover great distance when the interval is long enough. Tide moves across a flat beach grain by grain, and the water reaches farther than any single push suggests. Each cycle deposits a little more, and the cumulative result extends beyond what one wave accomplishes. The motion does not announce itself, and it does not require speed to be complete. Given sufficient time, the slow process fills the available space. Hart's paper appeared in the Quarterly Journal of the Royal Astronomical Society in 1975. He titled it, An Explanation for the Absence of Extraterrestrials on Earth, and he kept the language plain. The argument followed Fermi's line of thought and added explicit figures for crossing times. Hart used estimates between 1 million and 100 million years for a full traversal, depending on assumptions about speed and pauses. Those intervals remained small when placed beside billions of years of galactic history. The publication gave the paradox a reference point that later authors could cite. At his desk, Hart worked with pencil and paper, as many theorists did. He did not claim to resolve the question, and he did not propose a new mechanism. The paper gathered existing numbers for stellar ages, galactic dimensions, and plausible propulsion, then arranged them in a single ledger. He tested variations in the assumptions and noted that the conclusion persisted. The exercise was one of accounting, not invention. It translated a conversation into a form that journals could hold. The conclusion remained straightforward. If expansion were possible at even a small fraction of light speed, the galaxy could be traversed many times over in its lifetime. The absence of evidence on Earth or in the solar system then implied that such expansion had not occurred. Hart listed four categories of explanation that might resolve the tension, and he did not press any single one. The paper ended without drama, and it invited further measurement rather than assent. Metals cool in a way that parallels the logic of the argument. Heat leaves gradually, and the surface temperature drops by small steps. Each step is unremarkable, and the overall change accumulates without a visible moment of transition. The cooling continues until the object approaches the temperature of its surroundings. The process requires no special intervention, only time and contact with a larger reservoir. Hart's timescales functioned in a similar manner, where modest rates produced large outcomes once the interval grew long enough. The paper circulated among astronomers and planetary scientists through the later 1970s. It did not create immediate observing programs, but it gave those programs a clearer justification when funding was discussed. The reasoning provided a numerical baseline against which null results could be interpreted. That baseline was not a proof of solitude. It was a measure of what absence would mean if the premises held. The distinction mattered to those designing searches. Hart's treatment removed anecdote from the discussion and replaced it with explicit spans of time. He avoided claims about biology or sociology and stayed with physics and geometry. The approach narrowed the debate to whether interstellar expansion was physically plausible at low speeds. If it was, then the silence pointed to some other bottleneck. If it was not, then the reasoning required revision. The paper held the line between those alternatives without choosing. There is a steadiness in how informal remarks become formal when they touch a measurement that can be checked. The remark itself does not gain authority, the numbers around it do. Hart's contribution was to place the remark beside figures that already existed in astrophysics texts. Once there, the comparison could be tested by others, and it could be refined as better data arrived. The process turned a memory into a parameter. The galaxy's disk spans about 100,000 light years, and its stars number in the hundreds of billions. Hart used round figures for both quantities because the conclusion did not depend on precise values. Even if the crossing required several tens of millions of years, the margin between that span and the galaxy's age remained large. The arithmetic tolerated uncertainty in speed, in the number of pauses, and in the definition of settlement. The robustness of the result was part of its influence. He did not argue that faster than light travel was necessary. The estimates assumed speeds between 1% and 10% of light speed, drawn from propulsion studies of the period. At those rates, a probe or a vessel would still require many years to reach nearby stars, and many more to cross the disk. The point was that many years remained available in abundance. The arithmetic did not demand urgency, it demonstrated abundance of time. Hart's categories of explanation were careful rather than exhaustive. They included physical impossibility, self-destruction, lack of interest, and absence. He did not endorse any category, and he noted that each carried assumptions that could be examined. The paper therefore served as a map of options rather than a claim of resolution. It allowed subsequent work to address each branch with separate data. The map itself became a reference. The idea that a process can be slow and still complete has analogies in other fields. Sediment settles a particle at a time, and cliffs form without any single moment of creation. A glacier advances by fractions of a meter per day, and valleys appear. The time scale that matters is the one belonging to the system, not the one belonging to the observer. Heart's crossing times belong to the galaxy, and the galaxy's clock ran on billions of years. The mismatch between human clocks and galactic clocks shaped the problem. University libraries received the journal issue, and copies reached departments where radio astronomy and planetary science overlapped. The paper did not settle debates, it sharpened them. Researchers who doubted interstellar expansion could point to the assumptions about longevity and motivation. Researchers who accepted the possibility could point to the arithmetic and ask for searches. The exchange remained civil because the numbers were explicit. Each side could name the term it disputed. Later authors refined Hart's estimates with more detailed models of expansion fronts and percolation. They considered pauses for resource use, for construction, and for cultural reasons. The refined models still produced crossing times that were short compared to galactic ages. The basic tension survived the addition of complexity. That persistence gave the paper its lasting place in the literature. It became a standard citation in discussions of the paradox. The remark from 1950 had traveled from a lunch table to a journal page. It did so without changing its content, only its context. The numbers that surrounded it were already present in textbooks, and Hart's work placed them side by side. The result was a compact statement that could be examined, criticized, and extended. The process illustrated how physics proceeds when a qualitative observation meets quantities that can be checked. The transformation required no new discovery, only arrangement. The brief note about absence had become a measured constraint. It did not prove loneliness. It defined what loneliness would look like if the premises about expansion held. The constraint could be tested by looking for evidence of past visitation, by searching for signals, and by modeling how expansion might fail. Each test would either narrow the possibilities or reveal an error in the premises. The paper left that work to others, and the others continued. Hart did not revisit the topic at length after the publication. The paper stood as a single contribution, and it entered the set of references that defined the problem for the next generation. It circulated quietly, as many technical papers do, and it was read by those who needed a formal statement of the timescale argument. The influence accumulated without announcement. The numbers continued to do their work in the background. Chapter 3: Cocconi and Morrison Choose a Frequency. A frequency of 1420 megahertz corresponds to a wavelength of about 21 centimeters. This value arises from a fundamental transition in neutral hydrogen. Astronomers had already mapped the line across the galaxy because the transition is common. The number itself is not arbitrary. It follows from quantum properties of the atom. It provided a natural reference that did not depend on any particular culture. Giuseppe Cocconi and Philip Morrison worked in physics and were familiar with both nuclear processes and astrophysical observations. Cocconi had spent time at Cornell, Morrison at MIT, and both moved easily between theory and practical questions. They were interested in whether interstellar communication could be approached as an engineering problem rather than as speculation. Their backgrounds allowed them to combine knowledge of receivers with knowledge of the interstellar medium. The combination led to a short note rather than a lengthy treatise. A tone can persist without variation for a long interval. It holds a single pitch, and it does not drift with the noise around it. In a room filled with softer sounds, such a tone draws attention not by loudness, but by steadiness. The ear learns to separate it from the background after a short time. The persistence itself becomes the distinguishing feature. The tone corresponded in the physical world to radiation from the spin flip transition of hydrogen. At 1420 megahertz, the emission appeared wherever neutral hydrogen gathered in clouds. Radio telescopes of the 1950s already recorded it as a background feature of the galaxy. Cocconi and Morrison noted that a transmitter placed near that frequency would stand out against natural processes. The choice used a universal constant rather than a cultural convention. Their paper appeared in Nature in September of 1959. It occupied less than 2 pages, and it stated the argument with economy. The authors suggested that a narrow band signal near the hydrogen line would be the most promising place to listen. They also suggested that a civilization wishing to be found might choose the same region. The note did not claim detection. It proposed a place to begin. In a university office, the draft took shape over several afternoons. Morrison wrote in longhand, and Cocconi checked the numbers for the hydrogen transition. They debated whether to include a wider range of frequencies or to keep the focus narrow. Keeping the focus narrow won, because clarity mattered more than completeness at the outset. The manuscript was typed, revised once, and sent to the journal. Morrison argued that any technical civilization would know the hydrogen line. Cocconi agreed and added that the line was already used for galactic mapping. Their conversation moved between chalkboard calculations and practical limits of receivers then available. The final version reflected that balance between ideal and feasible. Hydrogen accounted for the majority of ordinary matter in the universe. Its abundance made the associated spectral line a common feature in radio surveys. The line at 21 centimeters penetrated interstellar dust with little absorption. That property allowed signals near the frequency to travel across the galaxy with modest attenuation. The physics therefore offered both a marker and a clear channel. A soft hiss fills the background of any sensitive receiver. It comes from many sources, and it varies slowly across frequency. Within that hiss, brief fluctuations appear and fade without pattern. The ear, or the electronic equivalent, learns the texture of the noise over time. Stateliness becomes noticeable because it contrasts with the random drift. The hiss continued across the microwave bands that radio astronomers explored in the 1950s. Against it, a narrow transmission would appear as a line that held its place while the background shifted. Cocconi and Morrison described this contrast as the reason to choose a narrow band. They noted that natural astrophysical processes rarely produce such narrow, stable features. The distinction turned a physical fact into a search strategy. Against that background, a transmitter of modest power could be detectable over interstellar distances if the bandwidth were narrow. The authors calculated that existing telescopes could already reach nearby stars under those conditions. They did not assume large antennas on the transmitting side, only that the signal would be concentrated. The conclusion followed from well understood noise temperatures and collecting areas. The proposal therefore moved the discussion from possibility to testability. There is a usefulness in choosing a constant that belongs to nature rather than to history. The hydrogen line does not change with language, calendar, or custom. It offers a common reference that any civilization with radio astronomy would encounter. That commonality does not guarantee contact, it only provides a place to listen first. Nature published the note on September 19th, 1959, under the title Searching for Interstellar Communications. The journal gave it prominent placement despite its brevity. Colleagues cited it quickly, and the idea entered graduate seminars within months. The paper contained no new physics, only a new application of known physics. Its influence came from the clarity of the recommendation. Frank Drake read the note while preparing for Project Ozma. He had already selected the hydrogen line as a listening frequency, and the paper confirmed the choice with independent reasoning. The convergence between theory and practice strengthened the case for early searches. Other groups adopted the same window for their first experiments. The frequency became a default starting point for the next decade. The suggestion remained. It waited for larger receivers and quieter sites. Later discussions expanded the concept to include the region between the hydrogen line and the hydroxyl lines near 1665 MHz. That interval became known as the water hole because it lay between the spectral signatures of H and OH. The name was metaphorical, and it pointed to the same logic of using abundant species as markers. The expansion did not replace the original suggestion, it widened it. Observers could search the original line first, then broaden the coverage. Universality in this context does not imply certainty of contact. It implies a shared starting point for two parties who have never met. The hydrogen line provides that starting point because it is accessible to anyone who builds a radio telescope. The choice reduces one source of mismatch without addressing the others. The note ended without predictions about success. It offered a frequency, a rationale, and a modest estimate of detectability. Observatories took the suggestion and built programs around it. The work that followed did not prove the presence of others. It defined where absence could be measured. The quiet that later accumulated began, in part, at 1420 MHz. Chapter 4. Frank Drake Writes 7 Terms. Frank Drake arrived at Green Bank in the spring of 1961 with a practical task. He had been asked to organize a small meeting on interstellar communication. The observatory offered a new 85-foot dish and a quiet valley. Drake brought with him experience from Project Ozma and a notebook of numbers. The meeting would gather a handful of scientists interested in turning speculation into measurement. The gathering was sponsored by the National Academy of Sciences and convened in November. Attendees included astronomers, biologists, and engineers who rarely shared a room. The agenda was open, and the central question remained how to estimate the number of detectable civilizations. Drake needed a structure that would allow discussion without drifting. He prepared a simple decomposition of the problem into sequential steps. Rooms in a house can serve as a way to hold separate ideas. Each room contains its own furniture, and passage from one to another requires a doorway. Light in one room does not determine the light in the next. A visitor moves through the sequence and notes what is present in each space. The arrangement allows complexity to be examined piece by piece. The terms of the discussion corresponded to such rooms. One held the rate at which stars form, another held the fraction that possess planets. A third contained the number of habitable worlds per system, and a fourth the fraction where life appears. Further rooms held the steps toward intelligence, toward technology, and toward longevity. The sequence allowed the group to assign numbers or ranges without conflating the stages. Drake wrote the decomposition on a blackboard at the front of the room. He labeled each factor and linked them with multiplication, indicating that the final number depended on all preceding ones. The board filled slowly, and the chalk marks remained visible throughout the meeting. Participants copied the structure into their notebooks. The equation itself was not the point, the separation of the problem was. At the board, Drake stood slightly to one side to keep the writing clear. He spoke in a level tone and paused between factors to allow questions. His handwriting was plain, and the symbols were large enough to be read from the back. When he reached the final term, he underlined it lightly. The gesture indicated that longevity might dominate the product. Otto Struve watched from the front row and nodded at the separation of astrophysical and biological steps. John Lilly asked about the definition of intelligence, and the group noted the difficulty without attempting resolution. The discussion returned to the board, where the structure held the conversation together. The meeting proceeded factor by factor, as Drake had intended. The first factor represented the average rate of star formation in the galaxy. Next came an estimate of the fraction of those stars that host planetary systems. A third step counted, on average, how many planets per system might support life. Following that, two factors addressed the emergence of life and the development of intelligence. Finally, the last pair considered the fraction that developed detectable technology and the lifetime of such civilizations. Dim light in a corridor makes edges soft and distances uncertain. Objects remain present, but their outlines blend with shadow. Movement continues, and the eye adjusts slowly to the reduced contrast. Details emerge gradually, and the scene becomes readable without becoming bright. The condition does not prevent navigation, it changes the pace. Uncertainty in each term behaved in a similar manner. The rate of star formation was relatively well measured, while the fraction of life-bearing planets remained dim. Intelligence and longevity were dimmer still, and the available data offered little contrast. Drake's structure allowed the group to see where light was strong and where it was weak. The dimness did not halt the work. It directed attention toward the factors most in need of measurement. Project Ozma had concluded the previous year with no detections from Tau Ceti or Epsilon Eridani. The null result was consistent with the new decomposition because the search had sampled only a tiny portion of the parameter space. The equation showed that even optimistic values for the early terms left vast uncertainty in the later ones. Drake used the Ozma experience to argue for broader frequency coverage and longer observing times. The meeting accepted the need for patience rather than for larger claims. Breaking a problem into stages changes the kind of work that follows. Instead of debating a single large number, researchers can address smaller questions with existing tools. Astronomy can improve the first terms, biology the middle ones, and engineering the later ones. The division does not solve the problem, it makes the problem manageable. Green Bank in 1961 provided a remote setting and a new instrument. The 85-foot telescope offered sensitivity that had not been available a decade earlier. Attendees included Dana Atchley, Carl Sagan, and Bernard Oliver, among others. Notes from the meeting recorded the 7 factors and the ranges discussed for each. The record became a reference for subsequent proposals to funding agencies. The influence of the meeting extended through the 1960s and into the NASA SETI studies of the 1970s. The decomposition appeared in textbooks and in review articles with minor variations in wording. Later authors added terms or combined them, but the sequential logic remained. The structure survived because it matched how different disciplines approached the question. It provided a shared language without requiring agreement on values. The board was erased at the end of the day. The structure remained in notebooks. Subsequent measurements improved the early factors substantially. The rate of star formation settled near a few per year, and the fraction of stars with planets approached unity after exoplanet surveys. Estimates for potentially habitable worlds per system remained less certain, and the biological terms stayed largely unconstrained. Longevity continued to dominate the overall uncertainty. The decomposition made that dominance visible. Patience in this context is not passive waiting. It is the continued refinement of terms that can be measured while acknowledging those that cannot. Drake's meeting modeled that patience by placing all factors on equal footing. The approach allowed progress without premature conclusions. The Green Bank meeting adjourned after 2 days. Participants returned to their institutions with copies of the 7 factors. No detection was announced, and no program was fully funded at that moment. The structure they carried home shaped proposals, observing plans, and later textbooks. The quiet that followed was not empty, it was organized. Chapter 5 Project Ozma Listens. In 1960, Project Ozma began at the National Radio Astronomy Observatory in Green Bank. The project took its name from the Queen of Oz, a choice meant to suggest a distant and perhaps imaginary realm. Frank Drake led the effort, and the goal was straightforward and limited. The telescope would listen to 2 nearby sun-like stars for signs of narrowband transmission. The work marked the first modern attempt to detect interstellar signals. The 85-foot dish had recently been commissioned and offered sensitivity at centimeter wavelengths. A receiver was built to cover a narrow band near the hydrogen line at 1420 MHz. The system recorded a single polarization and a bandwidth of a few hundred hertz, Drake and his small team calibrated the equipment during daylight hours. Observations were scheduled for times when the target stars rose above the local horizon. An ear at a keyhole gathers sound without entering the room. It remains outside, and it listens for a tone that persists amid softer noises. The posture is one of waiting rather than searching broadly. Attention narrows to a small opening, and the rest of the space recedes. The method trades coverage for sensitivity. The posture corresponded to Ozma's strategy. The telescope pointed at one star at a time and listened in a narrow channel. By design, most of the sky remained unexamined during the run. It relied on the assumption that a transmitting civilization might choose a natural frequency. The ear at the keyhole was therefore a deliberate limitation. Tau Ceti lay about 11.9 light years distant, and Epsilon Eridani about 10.5. Both stars resembled the Sun in mass and age, and both were close enough for modest transmitters to be detectable. Drake selected them for proximity rather than for any known planets. At the time, no exoplanets had been confirmed, and selection relied on stellar similarity. The pair provided a manageable starting sample. At the console, Drake adjusted the local oscillator and watched the chart recorder trace a steady line. The room remained dim to preserve night vision, and the hum of equipment filled the background. He noted the time, the frequency setting, and the sky conditions in a logbook. Each observation lasted several minutes before the system stepped to the next channel. The routine proceeded without interruption through the early hours. Night shifts followed a regular pattern of pointing, calibrating, and listening. Between targets, the team checked the receiver temperature and recorded interference from terrestrial sources. When dawn approached, the telescope was stowed and the tapes were labeled. The work accumulated in small increments rather than in dramatic moments. The receiver covered a band centered near 1420 MHz with a resolution that allowed narrow signals to stand out. A reference load provided calibration, and a switch alternated between sky and load several times per second. Output was integrated and written to analog charts, and later to magnetic tape. Sensitivity was sufficient to detect a transmitter of modest power within a few light years. The design reflected the technology available in 1960. A breath lasts only a few seconds and then passes. It marks time without effort, and it repeats without drawing attention. In the span of a night, many breaths accumulate, and the total remains brief against longer cycles. The measure is useful because it is familiar and finite. It provides a human scale for intervals that otherwise feel abstract. That brevity corresponded to Ozma's total observing time of about 150 hours. Spread across several months, the hours amounted to a short sample of the available sky and frequency space. The project listened to two stars in one narrow band, and the coverage remained correspondingly small. Drake recorded the total without exaggeration, noting the limits explicitly. The brief breath established a baseline rather than a conclusion. No signals exceeded the detection threshold in a manner consistent with an interstellar origin. Occasional bursts appeared, and follow-up showed them to be terrestrial interference or instrumental effects. The team applied simple tests, including switching frequencies and repointing, to discriminate. Each candidate faded under scrutiny, The final log contained no confirmed detections. There is a clarity that comes from a first limit. It does not answer the larger question. It defines how much remains to be examined. Ozma's 150 hours showed that listening was technically feasible. The limit also showed how much sky and bandwidth lay untouched. Between April and July of 1960, the observations accumulated in evening sessions. Weather and maintenance reduced the usable time, and the total settled near 150 hours. Logs recorded each session with start times, frequencies, and sky conditions. The data were preserved on tape and in notebooks. The archive later served as a reference for sensitivity calculations. The experience shaped the design of later searches. Engineers increased bandwidth, added polarizations, and improved interference rejection. Astronomers expanded target lists from 2 stars to hundreds and then thousands. The principle of starting narrow and then widening remained. Ozma provided a template that others could scale. It ended. The method continued. The limitations were plain and were acknowledged at the time. A single frequency near the hydrogen line could miss transmissions elsewhere. Two nearby stars represented a minuscule sample of the galaxy. The observing time covered only a small fraction of a year. The constraints were not failures, they were boundaries of a first attempt. Null results in this context function as measurements rather than as disappointments. They establish how much parameter space has been examined and at what sensitivity. Patience follows naturally when the remaining volume is large. Ozma demonstrated that patience could be organized into schedules and logs. The data sheets were filed, and the telescope returned to other programs. No announcement of detection was made, and none was expected by the team. The project entered the literature as a brief report and as a precedent. Its value lay in showing that the search could be conducted with existing tools. The quiet recorded in those 150 hours became the first measured point in a much longer curve. Chapter 6: The NASA Years and the Early Surveys. Because Ozma had shown that listening was technically feasible, interest moved from demonstration to design. Engineers and astronomers began to discuss what a larger search would require. The conversation shifted from whether to listen to how to listen efficiently. Funding agencies asked for estimates of cost and time. The groundwork for a more systematic program started to form. Workshops convened in the early 1970s under NASA sponsorship. Participants gathered at Ames Research Center and at other laboratories. Discussions covered antenna arrays, receivers, and data processing. Notes from the meetings emphasized the need for broad frequency coverage and for automated signal recognition. The tone remained practical rather than speculative. Shelves fill gradually when volumes are added one at a time. Each edition occupies a small space, and the overall collection grows without sudden change. Labels accumulate on spines, and the order of the shelves reflects the order of arrival. A visitor can trace the growth by noting the dates on the bindings. The process is incremental and quiet. Over time, the shelves corresponded to the archive of early SETI observations. Each survey contributed tapes, logs, and summary reports. The material did not contain detections. It contained limits and calibrations. Researchers could consult the shelves to see what frequencies had been examined and to what sensitivity. The archive grew in the manner of a library rather than a laboratory. The Cyclops report, completed in 1971, summarized the workshop conclusions. Barney Oliver of Hewlett-Packard led the study, and a team of engineers contributed detailed designs. The document proposed an array of many dishes working together to survey the sky. It outlined signal processing requirements and estimated costs. The report became a reference for later planning. In a conference room at NASA Ames, Oliver presented the Cyclops findings to a mixed audience. He used view graphs with block diagrams and cost curves. His delivery remained even, and he paused to allow questions about antenna numbers and computing loads. The room held engineers accustomed to large projects and astronomers accustomed to limited budgets. The presentation bridged those perspectives without forcing agreement. Oliver noted that the array could be built in stages, starting with a modest number of elements. He emphasized that the design allowed expansion as funding became available. Listeners asked about interference and about data storage, and he answered with estimates drawn from contemporary systems. The discussion ended with a consensus that the technical path was clear, even if the resources were not. The design called for hundreds of dishes, each steered electronically, feeding a central correlator. Signal processing would search for narrowband carriers and for pulses with artificial characteristics. The system required substantial computing power for the era, and the report included projections for future improvements. Cost estimates placed the full array beyond immediate budgets. The study therefore recommended phased implementation. Light in a room can be lowered gradually without a single switch being thrown. The change is noticed only when a page becomes harder to read. Shadows lengthen, and the edges of objects soften. Activity continues, but at a slower pace. The dimming does not end the work, it alters the conditions. The dimming corresponded to fluctuations in political support for SETI within NASA. Budgets rose and fell with changing priorities, and the program adjusted accordingly. During periods of reduced funding, work continued at a lower level in university laboratories. The community maintained momentum through small surveys and theoretical studies. The light remained low, but it did not go out. NASA established a formal SETI effort at Ames Research Center in the mid-1970s. The program focused on developing signal detection algorithms and on conducting targeted searches. Engineers built prototype hardware, and astronomers compiled target lists. The work proceeded in parallel with the larger Cyclops vision. Progress accumulated in reports and in incremental improvements to receivers. Continuity in such circumstances survives through interruption. Small groups preserve methods, and they maintain archives between periods of larger support. The knowledge does not disappear when budgets contract. It moves to different shelves. The pattern allows a field to resume without starting anew. In 1978, Senator William Proxmire included the NASA SETI effort in his Golden Fleece Awards. The designation drew public attention and contributed to a reduction in funding. The program was not terminated, but its scope was curtailed. Work continued at a reduced pace, and some activities shifted to private support. The episode illustrated how political visibility could alter technical schedules. University groups sustained observations through the late 1970s and into the 1980s. The Ohio State Big Ear continued sky surveys, and Harvard conducted targeted searches with modest equipment. Each effort added hours of coverage and refined techniques for interference rejection. Results remained consistent with earlier null detections. The combined data expanded the archive described earlier. The program paused. The archive did not. The archive grew to include thousands of hours of observations across multiple frequencies. Analysts used the material to calculate upper limits on the prevalence of strong transmitters. Those limits were expressed as fractions of stars surveyed to a given sensitivity. The numbers remained preliminary, but they provided a quantitative context for future work. The slow accumulation of non-detections became a measurable quantity. Incremental work in this field resembles the filling of shelves. Each survey adds a volume, and the collection becomes useful only after many additions. The value lies not in any single tape, but in the aggregate. That aggregate allows later researchers to speak about what has been examined. By the mid-1980s, the technical roadmap from Cyclops remained on file, and the archive of observations continued to expand. NASA's formal effort had been reduced, but university programs maintained a baseline of activity. The community carried forward methods for calibration, for interference rejection, and for data archiving. This period did not produce a detection, it produced a foundation. The quiet recorded in those years became the basis for the larger searches that followed. Chapter 7: The Wow Signal. A brief rise in intensity appeared on a computer printout on the evening of 15 August 1977. The trace climbed above the background and then declined in a smooth curve. Its shape matched what would be expected from a distant point source drifting through a telescope beam. The event lasted a little more than a minute. A record of the passage was preserved on a strip of folded paper. The Ohio State University Big Ear Radio Telescope conducted a sky survey in drift scan mode. The instrument used a fixed reflector and relied on Earth's rotation to sweep the beam across the sky. Data were recorded as alphanumeric characters representing signal strength. The survey operated at a frequency near the hydrogen line. The system was designed to detect narrowband signals of possible artificial origin. A flare in twilight brightens briefly and then fades without altering the sky. It draws attention because of the contrast, not because of duration. Observers note the rise, the peak, and the return to previous levels. The event leaves no debris, only a memory of the change. The briefness itself becomes the defining characteristic. The flare corresponded to the pattern recorded by Big Ear on that August night. Intensity rose over several seconds, reached a maximum, and then declined symmetrically. Duration matched the time required for the telescope's beam to cross a fixed point on the sky. At approximately 72 seconds, the width fit the instrument's known response. The shape suggested a source beyond the Earth rather than local interference. The detection occurred at a frequency near 1420-4556 MHz, close to the hydrogen line. A receiver channel recorded the signal, and the strength reached a level designated as 6 EQA, a high value on the printout scale. Coordinates placed the source in the direction of the constellation Sagittarius. No modulation was evident in the limited data, and no information content could be extracted. The observation remained a single point in time and frequency. In the laboratory a few days later, Jerry Eamon reviewed the printouts from the survey. He worked through stacks of folded paper, marking routine variations and noting interference. When he reached the strip from 15 August, he paused at the sequence of characters indicating high intensity. He circled the code and wrote a brief annotation in the margin. The annotation consisted of a single word. Eamon recognized the pattern as consistent with the expected signature of a celestial source. He did not claim a discovery, and he noted the need for confirmation. The word he wrote expressed surprise rather than conclusion. Colleagues later reproduced the annotation in discussions of the event. The Big Ear operated without a steerable dish, and its beam pattern was well characterized. A source crossing the beam would produce a rise and fall lasting about 72 seconds. The WOW signal matched that duration closely. Two beams were recorded, separated slightly in time, and the signal appeared in only one, as expected for a localized source. Characteristics aligned with an astronomical origin, though they did not prove it. An echo in a large space returns once and then diminishes. It does not repeat with the same strength, and the later returns blend into background noise. The initial sound remains clear in memory, while subsequent listening yields only the room tone. The absence of repetition does not erase the first event. It places the event in isolation. The echo corresponded to the subsequent history of the WOW signal. Observations of the same region were conducted many times in the following months and years. No repetition at the same frequency and position was found. The original detection remained alone in the archive. The fading of later attempts left the first record isolated. Follow-up observations used the Big Ear and other telescopes, including searches at Green Bank and elsewhere. Teams pointed at the coordinates and listened at and near the original frequency. Sensitivity improved with newer receivers, and integration times increased. Despite many hours of coverage, no matching signal appeared. The null results did not disprove the original event, they established its singularity. A single point stands out in a field that is otherwise uniform. It draws attention not because it is loud, but because it is different. In a long survey of quiet, one deviation becomes a reference. The WOW signal functions in that way within the history of listening. On the evening of 15 August, the local time at the observatory was near 10:16 p.m. Eastern Daylight Time. Frequency was recorded as 1420-4556 MHz, slightly offset from the exact hydrogen line due to receiver settings. Duration of 72 seconds matched the beam transit time. Intensity reached code 6 on the scale used by the computer. These numbers were preserved in the original printout and in later transcriptions. Newspapers reported the event years after its occurrence, once the annotation became widely known. Popular accounts emphasized the word written in the margin and the mystery of non-repetition. Scientific articles treated the signal as an unconfirmed candidate and listed possible natural and artificial explanations. The discussion remained cautious and it avoided claims beyond the data. The public interest persisted because the record was simple and visual. The signal did not return. The record remained. Later studies examined cometary hydrogen clouds, satellite transmissions, and instrumental effects as possible origins. None provided a complete match to the observed strength, duration, and frequency. The comet hypothesis received attention in 2017 and was subsequently questioned on grounds of brightness and motion. Interference from Earth orbiting platforms remained unlikely given the frequency and beam pattern. The origin stayed undetermined. Solitary events in science occupy a particular role. They cannot support broad conclusions, and they cannot be dismissed without examination. Such events persist as markers of what was seen once under specific conditions. The wow signal remains in that category. By the early 1980s, the printout with the circled characters had been copied and discussed in many settings. The original tape containing the raw data had been reused, as was common practice at the time. The paper record therefore became the primary source. Researchers continued to reference the event in reviews of SETI history. The brief rise recorded on that August night stayed in the archive as a single, unrepeated point. Chapter 8: Project Phoenix. The Parkes radio telescope in Australia and the Arecibo dish in Puerto Rico provided the foundation for Project Phoenix. Instruments of that size were not built for SETI, but they offered sensitivity that smaller dedicated arrays could not match. The project used existing facilities through negotiated observing time. Its approach allowed a targeted search without constructing new hardware. The choice reflected a practical balance between capability and cost. Project Phoenix began in 1995 under the SETI Institute. The effort followed earlier NASA work and continued after federal funding decreased. Its goal was to examine nearby sun-like stars across a wide frequency range. The search emphasized depth over breadth, spending significant time on each target. Designers intended the program to produce quantitative upper limits rather than anecdotal reports. A garden is planned before it is planted. Rows are spaced to allow light, and species are chosen for compatibility with soil and climate. The gardener selects for age, for hardiness, and for the likelihood of sustained growth. The arrangement reflects intention rather than chance. The result is a collection that can be tended systematically. The garden corresponded to the target list assembled for Phoenix. Stars were chosen for stability, for age similar to the Sun, and for proximity. The list excluded active binaries and very young stars prone to flares. Approximately 800 targets were selected, each with known coordinates and spectral types. The careful selection allowed observing time to be used efficiently. Jill Tarter led the selection process and the overall observing strategy. She drew on catalogs of nearby stars and on knowledge of stellar evolution. Criteria emphasized main sequence stars with ages of several billion years. The team also included a smaller sample of stars with known planetary systems as they became available. The approach balanced completeness with practicality. In a conference room at the SETI Institute, Tarter spread charts of the solar neighborhood across a table. She marked distances, spectral types, and ages with colored pens. Colleagues suggested additions and removals based on updated parallaxes. The discussion moved slowly, with each star considered individually. The list grew incrementally rather than in large batches. Tarter argued for prioritizing stars similar to the Sun, while retaining a fraction of diverse types for comparison. She noted that stability over billions of years increased the chance for biological evolution. The group accepted the compromise and recorded the final selection. The resulting catalog guided the observing schedule for the next decade. Observations ran from 1995 to 2004, using time allocated at Parkes, Green Bank, and Arecibo. The receivers covered frequencies from about 1,000 to 3,000 megahertz with narrow channel resolution. Each target received multiple looks, often totaling tens of minutes per star. Calibration observations bracketed the science data. The system recorded both polarizations where possible. A watch kept through a night proceeds by steady attention rather than by sudden action. The observer remains seated, and the environment changes slowly around them. Minutes accumulate, and the task continues without variation. The work does not demand haste, it demands persistence. The value emerges from duration rather than from intensity. The watch corresponded to Phoenix observing sessions that extended over many hours. Telescopes tracked targets as they rose and set, and data accumulated continuously. Operators monitored for interference and adjusted thresholds as conditions changed. The routine produced long integrations that improved sensitivity. The patient watch allowed faint signals to become detectable if present. No confirmed extraterrestrial signals were identified in the Phoenix data. Occasional candidates appeared, and follow-up observations showed them to be terrestrial or instrumental. The team applied standard tests, including reobservation and off-source pointing. Each candidate faded under scrutiny. The final archive contained no persistent detections. Selection shapes the limits that a survey can claim. By choosing nearby sun-like stars, Phoenix could set meaningful upper bounds on the prevalence of strong transmitters. A different target list would have produced different constraints. The care in selection, therefore, became part of the scientific result. Between 1995 and 2004, Phoenix observed approximately 800 stars. Observations at Parkes covered southern targets, while Arecibo and Green Bank covered northern skies. The combined effort totaled several thousand hours of telescope time. Frequency coverage spanned the so-called microwave window favored for interstellar communication. The dataset represented the most sensitive targeted search of its era. Data streams were processed in near real time to flag narrowband features. Algorithms searched for drifting tones consistent with relative motion between transmitter and receiver. Interference rejection relied on simultaneous observations and on comparison with known terrestrial sources. Human analysts reviewed candidates that survived automated filters. The pipeline balanced completeness with manageable false positive rates. The program concluded in 2004. The archive remained. Results were published as upper limits on the fraction of stars hosting detectable transmitters. The limits depended on assumed transmitter power and duty cycle, and they were presented for a range of plausible values. For strong, continuously radiating sources, the data excluded their presence around most nearby sun-like stars. For weaker or intermittent sources, the constraints were less stringent. The publications provided a quantitative baseline for future searches. Systematic searches demonstrate what targeted observing can achieve with existing instruments. They show that depth on a limited sample complements breadth across the sky. Phoenix illustrated that a well-chosen target list and long integrations produce meaningful constraints even without detections. The method became a model for subsequent programs. By 2004, the dishes returned to other astronomical programs, and the Phoenix team archived the final data products. No announcement of detection was made, and none had been expected as a likely outcome. The project entered the literature as a demonstration of feasibility and as a source of limits. Its value lay in the careful selection of targets and in the disciplined accumulation of observing time. The quiet measured around 800 nearby stars became part of the larger curve of non-detections. Chapter 9: The Allen Telescope Array. The Allen Telescope Array was constructed in Northern California to conduct wide-field radio surveys. The facility was designed from the outset to support SETI alongside other astrophysical programs. Its architecture emphasized many small dishes rather than a single large aperture. The approach allowed flexible scheduling and simultaneous observations. The array represented a shift toward dedicated, continuous listening. Funding for the project came from philanthropist Paul Allen, whose support enabled construction to proceed in phases. The site at Hat Creek Radio Observatory offered radio quiet conditions and existing infrastructure. Planning began in the early 2000s, and construction followed a modular design. The partnership between the SETI Institute and the University of California provided scientific direction. The goal was to build an instrument that could observe continuously. Ears distributed across a field can listen in many directions at once. Each ear receives its own portion of sound, and the combined information exceeds what a single ear can gather. The arrangement allows a listener to monitor several conversations without moving. Separation improves the ability to distinguish sources. The configuration trades size for multiplicity. The ears corresponded to the dishes of the Allen Telescope Array. Each 6-meter antenna collected radiation independently, and signals were combined digitally. The array could form multiple beams on the sky simultaneously. That capability allowed SETI observations to proceed while other astronomical programs continued. The design embodied the principle of many modest collectors working together. The initial array comprised 42 dishes, with infrastructure planned for expansion. The number was chosen to balance cost and survey speed. Correlators processed the incoming data streams and formed beams in software. The system operated over a wide frequency range, from below 1 GHz to above 10. The flexibility supported both targeted SETI and surveys for transient phenomena. In October 2007, the array achieved first light. Engineers pointed a subset of dishes at a bright calibrator and recorded fringes. Data appeared on monitors in the control building at Hat Creek. The team verified pointing, focus, and correlation. The moment marked the transition from construction to operation. Early operations focused on commissioning and on initial SETI observations. Jill Tarter and colleagues scheduled observations of nearby stars drawn from earlier target lists. The array observed while software pipelines were refined. Performance improved incrementally as more dishes were added to the correlator. The system covered frequencies from approximately 1 to 11 gigahertz in its early configuration. Receivers were designed for wide bandwidth and for rapid retuning. Signal processing searched for narrowband tones and for pulsed features. The architecture allowed simultaneous SETI and imaging observations. The dual use increased the scientific productivity of the facility. Threads woven together create a fabric stronger than any single strand. Each thread follows its own path, and the crossing points define the pattern. The weaver maintains tension across many threads simultaneously. The result holds together because the individual elements are coordinated. The process illustrates how multiplicity can produce unity. The weaving corresponded to the array's ability to form multiple beams. Each beam sampled a different direction, and the correlator maintained coherence across dishes. The pattern allowed the telescope to monitor several targets or to map a region efficiently. That parallelism increased the rate at which parameter space could be examined. The approach changed the economics of long-duration searches. No extraterrestrial signals were confirmed during the early years of operation. The array recorded the expected background of galactic synchrotron emission and terrestrial interference. Candidates appeared, and follow-up observations showed them to be of local origin. The data contributed to upper limits on the prevalence of strong transmitters. The null results were consistent with earlier targeted searches. Parallelism changes the character of a search. Instead of choosing one target at a time, an array can monitor many directions concurrently. The trade is increased complexity in correlation and data handling. The benefit is a faster accumulation of coverage without proportional increases in time. At Hat Creek, the initial 42 dishes stood on concrete piers arranged across the site. Construction had begun in 2004, and first light followed in 2007. Paul Allen's support allowed the project to reach initial operations and to demonstrate the concept. The location offered shielding from radio interference by surrounding terrain. The facility operated as a partnership between the SETI Institute and university researchers. The SETI Institute provided scientific leadership for the SETI program on the array. Jill Tarter and her colleagues adapted target lists from Project Phoenix and expanded them. Observing schedules interleaved SETI pointings with surveys for pulsars and transients. The shared use maximized the scientific return from the instrument. The collaboration demonstrated how a dedicated array could serve multiple communities. First light passed. Operations continued. Operations encountered funding constraints and technical challenges typical of new arrays. Maintenance of many small dishes required regular attention, and correlator upgrades proceeded in stages. Despite interruptions, the array accumulated observing hours for SETI and for astrophysics. Data from the period contributed to studies of transient radio sources. The experience informed designs for future expansion. Dedicated instruments alter expectations about continuity. A facility built for long-term monitoring can operate through seasons and years without reallocation. The steady accumulation of data becomes a resource in itself. The Allen Telescope Array embodied that principle in its design and operation. By the early 2010s, the array had demonstrated simultaneous multi-beam observing and wideband processing. No confirmed technosignatures had been found, and the archive grew with calibrated data. The facility continued to serve as a testbed for signal detection algorithms. Its operation showed that a modest array of many dishes could sustain a continuous search. The quiet recorded at Hat Creek joined the larger record of non-detections. Chapter 10: Breakthrough Listen. A commitment of $100 million was announced in July 2015 for a new search program. Funding was intended to support a decade of observations at major radio facilities. The scale exceeded previous privately funded efforts by a large margin. The program was named Breakthrough Listen. Organizers emphasized open data and systematic coverage. The initiative was launched by investor Yuri Milner with scientific leadership from the Breakthrough Initiatives Board. Its goal was to conduct the most comprehensive search for technosignatures to date. Planners allocated observing time at the Green Bank Telescope and at Parkes Observatory. Later agreements added the Meerkat Array in South Africa. The structure combined private funding with public facilities. An aperture widened gradually allows more light to enter without changing the lens. The increase is measured in area, and the gain accumulates across the surface. Objects that were previously faint become accessible, and the field of view remains steady. The change does not alter the sky, it alters the capacity to record it. The widening proceeds quietly, without announcement. The widening corresponded to the infusion of dedicated observing time for Breakthrough Listen. Telescopes that previously allocated occasional hours could now schedule thousands of hours. The increase allowed deeper integrations and broader frequency coverage. Sensitivity improved not through new physics, but through sustained access. The resource expanded the aperture in a practical sense. The program secured time on the 100-meter Green Bank Telescope in West Virginia and on the 64-meter Parkes dish in Australia. Both facilities offered receivers covering gigahertz of bandwidth. The partnership with Meerkat later provided an array capability in the Southern Hemisphere. Observations were scheduled in blocks, often lasting many hours per target field. The arrangement ensured continuous data collection across seasons. On the first night at Green Bank, the team pointed the telescope toward a nearby star from the initial target list. Operators loaded the observing script and verified receiver tuning across the band. Data flowed to storage servers in the control building. The room remained quiet except for the hum of cooling fans. The session proceeded through calibration and into science observations. Astronomers monitored the incoming spectra for narrowband features and for drifting tones. When a candidate appeared, the system automatically scheduled a reobservation. The first night produced no confirmed detections, and the team logged the results. The routine established the pattern for subsequent runs. The survey aimed to observe on the order of 1 million nearby stars, along with selected galaxies and the galactic plane. Frequency coverage spanned from approximately 700 megahertz to tens of gigahertz. The strategy combined targeted pointings with wide area scans. Data rates reached tens of gigabytes per second at peak. The scale required automated processing pipelines. A flood moves through a channel and fills the surrounding basin. Water spreads evenly and the level rises without sudden steps. The flow continues for an extended interval and the volume accumulates. Observers measure the increase by marks on a gauge. The process is steady rather than dramatic. The flood corresponded to the data produced by Breakthrough Listen. Petabytes accumulated over years of observing, stored on disks and tapes at multiple sites. The volume exceeded that of earlier SETI programs by orders of magnitude. Analysts developed tools to search the flood for narrow features. The steady accumulation became a resource for the community. No confirmed technosignatures were identified in the initial years of the program. Candidates were examined, and follow-up observations showed them to be terrestrial interference or instrumental artifacts. The team published null results along with descriptions of methods. A public data archive was released for independent analysis. That openness allowed external researchers to reproduce the searches. Resources change the pace at which a field can work. Dedicated time removes the need to compete for occasional hours. Sustained access allows deeper searches and broader coverage. The shift does not guarantee detection, it guarantees measurement. In July 2015, the announcement specified a 10-year program with $100 million of support. Green Bank and Parks were named as primary facilities, with Meerkat added through later collaboration. That commitment enabled thousands of hours per year on large telescopes. Partnership with the University of California, Berkeley provided data analysis expertise. The scale represented a step change in SETI resources. Data from the program were made available through an open archive with calibrated spectra and metadata. Documentation described observing setups, frequency ranges, and sensitivity estimates. Researchers outside the core team downloaded portions of the archive for independent searches. Workshops and tutorials supported community use. The practice of open data became a standard for subsequent efforts. The pledge matured into observing time. The observing time matured into data. Limits derived from Breakthrough Listen data were expressed as fractions of stars surveyed to specific sensitivities. For nearby targets, the observations excluded the presence of powerful beacons. For more distant or intermittent sources, constraints were weaker but still quantifiable. The results shifted discussion from anecdote to statistics. The conversation increasingly referenced hours observed and bandwidth covered. Scale in this context does not imply certainty. It implies the ability to state what has been examined and to what depth. Breakthrough Listen provided that statement across a large parameter space. The clarity allowed the field to plan next steps based on measurement rather than assumption. By the early 2020s, the program had accumulated thousands of hours at Green Bank, Parks, and Meerkat. No confirmed extraterrestrial signals had been found, and the archive continued to grow. The effort demonstrated what sustained funding could achieve with existing telescopes. Its legacy included both the data and the model of open, systematic searching. The quiet recorded in those years joined the cumulative record of the sky. Chapter 11: Exoplanets Change the Context. The discovery of thousands of exoplanets began in earnest with the Kepler mission. A spacecraft monitored stellar brightness for periodic dips indicative of transits. Its method allowed detection of planets ranging from larger than Jupiter to smaller than Earth. Early results suggested that planets were common rather than rare. The finding altered the context for discussions of life beyond the solar system. Kepler launched in 2009 and operated from an Earth-trailing orbit. The telescope stared at a single field in Cygnus and Lyra for 4 years. Photometers recorded brightness variations with high precision. Data were transmitted to Earth and processed into light curves. The design prioritized statistical completeness over individual discoveries. Seeds scattered across soil settle according to wind and terrain. Some land in clusters, others remain isolated. Germination depends on conditions that vary across the field. The distribution reflects both abundance and suitability. The pattern emerges only after many seasons of observation. The seeds corresponded to planets detected by Kepler across its field of view. Each detection represented a world orbiting a distant star. The distribution showed that small planets outnumbered large ones. Occurrence rates approached 1 planet per star on average. The abundance became a measurable quantity rather than a speculation. By 2013, Kepler had identified several thousand planet candidates, with more than 2,000 later confirmed. Statistical analyses accounted for detection efficiency and geometric alignment. Results indicated that approximately 20% of Sun-like stars host an Earth-sized planet in the habitable zone. The fraction for all planets, regardless of size, approached unity. The numbers provided the first robust estimates for the early terms of the Drake equation. In March 2009, Kepler launched aboard a Delta II rocket from Cape Canaveral. Engineers monitored telemetry as the spacecraft separated and deployed its solar arrays. The telescope cover opened weeks later after outgassing. Commissioning observations verified pointing stability and photometric precision. The mission entered science operations in May. Early data revealed transit signals within weeks of operation. The team validated candidates with follow-up observations from ground-based telescopes. False positives were identified and removed through careful analysis. The catalog grew steadily as the mission continued. Later missions extended the census of exoplanets. The Transiting Exoplanet Survey satellite, launched in 2018, surveyed the entire sky for nearby transiting worlds. Radial velocity surveys from ground-based spectrographs measured planet masses. Combined data refined occurrence rates for planets of different sizes and orbital periods. The emerging picture confirmed that planetary systems are the norm rather than the exception. A temperate band around a heat source maintains conditions between extremes. Within the band, temperatures allow liquid water to persist. The width depends on the output of the source and on atmospheric properties. Boundaries are not sharp, they transition gradually. The band provides a useful reference for habitability. The band corresponded to the circumstellar habitable zone defined for exoplanet studies. Kepler data allowed estimation of the frequency of Earth-sized planets within that zone. The term eta Earth emerged to describe that occurrence rate. Measurements placed the value on the order of a few tenths for sun-like stars. The concept provided a quantitative anchor for discussions of life. The abundance of planets shifted the early factors in the Drake equation from speculation to measurement. The fraction of stars with planets approached 1, and the number of potentially habitable worlds per system became estimable. Uncertainty remained, but the range narrowed substantially. The shift moved the bottleneck in the equation toward later terms involving biology and longevity. The silence of the sky therefore carried more weight. Abundance sharpens a question rather than resolving it. When planets prove common, the absence of detectable civilizations points more clearly to later stages. The focus moves from whether worlds exist to whether life and technology arise and persist. The clarification does not answer the paradox, it refines its location. Data from Kepler, published between 2010 and 2015, established that small planets are ubiquitous. Occurrence rates indicated roughly one planet per star on average, with many stars hosting multiple planets. The mission detected thousands of candidates, and subsequent validation confirmed the statistical trends. Findings became a foundation for later SETI target selection. The shift in context made the lack of detections more informative. If habitable planets are common, then the absence of signals suggests that fewer civilizations reach detectability or remain detectable for long intervals. The early terms of the Drake equation no longer dominate the uncertainty. Later terms, particularly longevity, gained prominence. The quiet therefore pointed toward biology, culture, or technology rather than toward planetary scarcity. Planets proved common. Signals did not. TESS continued the work by surveying nearby bright stars, facilitating follow-up characterization. Ground-based spectrographs measured masses and densities, refining habitability assessments. Statistical studies combined Kepler and TESS data to improve occurrence rates. The combined dataset supported estimates of eta Earth with reduced uncertainty. The measurements informed the selection of targets for Breakthrough Listen and other programs. If planets are abundant, the bottleneck must lie later in the sequence from world to detectable civilization. The possibilities include the rarity of life, the rarity of intelligence, or the brevity of technological phases. Each possibility carries different implications for search strategies. The abundance of worlds makes the distinction testable in principle. By the early 2020s, the occurrence of planets was no longer a matter of debate. Focus shifted toward understanding the later terms that remained uncertain. The quiet persisted despite the abundance of potential habitats. Data from Kepler and its successors provided a quantitative backdrop for that quiet. That abundance made the silence more specific and more instructive. Chapter 12: Fast radio bursts enter the scene. A millisecond flash of radio emission appeared in archival data from the park's telescope. The pulse arrived in 2001, but it was recognized in 2007. Its duration was less than 5 milliseconds, and its brightness exceeded the background by a large factor. The dispersion of the signal indicated an extragalactic origin. The event became known as the Lorimer burst. The discovery was made by Duncan Lorimer and colleagues while searching for pulsars. They examined data recorded years earlier and noticed a single dispersed pulse. That signal did not repeat in the available observations. The team published the finding and suggested a cosmological distance. Their report introduced the term fast radio burst. A spark in darkness appears suddenly and vanishes quickly. It illuminates the immediate surroundings for an instant. The brief light draws attention because of contrast rather than duration. Afterward, the scene returns to its previous state. The memory of the spark persists longer than the light itself. The spark corresponded to the behavior of fast radio bursts. Each burst arrived as a brief, intense pulse in radio frequencies. The duration, typically milliseconds, matched the timescale of the spark analogy. Observers recorded the arrival time, dispersion measure, and fluence. The event stood out against a background of steady noise. The burst showed a dispersion measure far exceeding that expected from the Milky Way. That excess indicated propagation through ionized material over cosmological distances. Implied energy, if isotropic, was comparable to that of the sun emitted over days. The source remained unidentified in the initial data. Properties suggested a new class of astrophysical transient. In 2007, Lorimer reviewed archival parks data on a workstation in West Virginia. He plotted pulse arrival times against dispersion measure and noticed an outlier. The point lay far from the cluster of known pulsars. He examined the raw data and confirmed the pulse shape. The finding was recorded and shared with collaborators. Duncan Lorimer and his student David Narkovich prepared a manuscript describing the event. They estimated distance from the dispersion and discussed possible origins. The paper noted the lack of repetition and the need for further searches. The publication prompted other groups to examine archival data. The Canadian Hydrogen Intensity Mapping Experiment, known as CHEAM, began operations in 2018 and greatly increased the detection rate. The telescope's wide field of view allowed continuous monitoring of the northern sky. Hundreds of fast radio bursts were detected within the first year. The sample included both one-off events and repeaters. The data enabled population studies and statistical analyses. A chamber with hard walls returns sound after the initial utterance. The echo arrives later and with reduced intensity. Repeated utterances produce a series of diminishing returns. The listener learns to distinguish the original from its reflections. The pattern reveals properties of the space. The chamber corresponded to the behavior of repeating fast radio bursts. Some sources emitted multiple bursts over days and months. Repetition allowed localization to host galaxies. Patterns of repeats varied between sources, with some showing periodicity. That ability to return to the same position distinguished repeaters from apparent one-off events. Initial reports noted the possibility of artificial origin for fast radio bursts. The brightness and brevity invited speculation. As more bursts were detected, natural explanations involving magnetars and other extreme objects gained support. The discovery of a repeating burst associated with a magnetar in the Milky Way strengthened the astrophysical interpretation. The artificial hypothesis receded as the population grew. Natural mimics shaped skepticism in searches for techno-signatures. When the sky produces bright, brief pulses without technology, the burden of proof for artificiality increases. Fast radio bursts provided a clear example of a natural process that initially appeared unusual. The lesson informed criteria for verification. The original detection occurred in data from 2001 and was published in 2007. Duration was approximately 5 milliseconds, and dispersion measure exceeded 300 parsecs per cubic centimeter. Chime began science operations in 2018 and detected hundreds of bursts. The events originated from distances ranging from nearby galaxies to cosmological redshifts. The sample demonstrated that millisecond radio transients are a common phenomenon. Verification of fast radio bursts required repetition and precise localization. Interferometric observations provided positions accurate to arcseconds. Host galaxies were identified, and redshifts were measured. The association with star-forming regions supported models involving young magnetars. The process illustrated the standards needed to confirm a new class of source. Bursts appeared. Explanations followed. Wide-field surveys demonstrated that unexpected phenomena emerge when large volumes of parameter space are examined. CHIM's daily coverage revealed the ubiquity of fast radio bursts. Other instruments found similar transients at different frequencies. The discoveries did not resolve the Fermi Paradox, but they showed that the sky remains capable of surprise. The lesson applied to SETI as well as to astrophysics. New classes of signal emerge from noise when sensitivity and coverage improve. Fast radio bursts followed that pattern, moving from a single archival event to a population. The trajectory illustrates how a rare phenomenon becomes routine with adequate instrumentation. The history informs expectations for future searches. By the early 2020s, fast radio bursts were recognized as natural, extragalactic transients. No evidence linked them to extraterrestrial technology. Models involving highly magnetized neutron stars accounted for the observations. The bursts remained relevant to SETI as examples of bright, brief signals that require careful verification. Their discovery underscored the importance of repetition, localization, and multi-wavelength follow-up. The sky's capacity to produce such sparks made the ongoing quiet more meaningful. Chapter 13: Oumuamua and Interstellar Visitors. An object moving on a hyperbolic trajectory was identified in October 2017. The orbit indicated an origin outside the solar system. The body was designated 1I 2017 U1 and later named Oumuamua. Its speed and trajectory confirmed interstellar provenance. The discovery marked the first confirmed visitor from another star system. The Pan-STARRS Survey Telescope on Haleakala detected the faint moving source during routine operations. The system recorded a series of images showing motion against background stars. Automated pipelines flagged the object for human review. Follow-up observations confirmed the unusual orbit. The Minor Planet Center announced the discovery within days. A ship passing a harbor does not stop, and it does not signal its origin. It moves steadily through the channel, visible for a limited interval. Observers on shore note its shape, its speed, and its direction. The passage provides a brief opportunity for measurement. Afterward, the vessel continues beyond the horizon. The ship corresponded to Oumuamua's traversal of the inner solar system. The object entered from above the ecliptic and departed on a hyperbolic path. Telescopes recorded its brightness variations and color. The brief visit allowed limited characterization before it faded. The passage resembled a transient visitor rather than a resident. The object exhibited an elongated shape inferred from large brightness variations. Estimates suggested an axis ratio of at least 5:1. The surface appeared reddish, consistent with irradiated organic material. No coma or tail was detected in deep images. The combination of properties was unusual among known solar system bodies. On the night of 19 October, the Pan-STARRS camera recorded a faint streak in successive exposures. The software identified motion inconsistent with main belt asteroids. An astronomer on duty reviewed the frames and initiated follow-up requests. Additional telescopes confirmed the high velocity. The data were compiled for orbit determination. Astronomers around the world scheduled observations as the object brightened. Photometric measurements tracked its rapid rotation. Spectroscopic data remained limited due to faintness. The community coordinated through circulars and shared data sets. Measurements of the trajectory revealed a small non-gravitational acceleration. The deviation was consistent with outgassing, though no coma was observed. Alternative explanations included radiation pressure on a low-density structure. The magnitude of the acceleration was modest, but statistically significant. The cause remained debated due to limited data. A faint push applied to a drifting body changes its path slightly over time. The effect accumulates, and the deviation becomes measurable after an interval. Its source may remain invisible to the observer. Motion itself provides evidence of the force. The push is inferred rather than seen. The push corresponded to the non-gravitational acceleration measured for Oumuamua. Magnitude was small, on the order of a few micrometers per second squared. Direction aligned roughly with the antisolar vector, consistent with outgassing. No direct detection of gas or dust accompanied the measurement. The inference relied on precise astrometry. Avi Loeb, then at Harvard, suggested that the unusual properties could be consistent with an artificial origin. The hypothesis proposed a thin reflective structure propelled by radiation pressure. Most astronomers favored natural explanations, citing the lack of direct evidence for technology. The discussion received broad media attention. The scientific literature continued to explore outgassing models and other natural mechanisms. Anomalies invite hypothesis because they fall outside established categories. When data are sparse, multiple explanations can fit the observations. The temptation is to favor the most novel interpretation. Discipline requires weighing plausibility against evidence. In October 2017, Pan-STARRS discovered the object later designated 1I 2017 U1. The interstellar trajectory was confirmed within days. Breakthrough Listen conducted radio observations with the Green Bank telescope in December 2017. The search covered multiple bands near the expected frequencies for artificial transmitters. No narrowband signals were detected above the sensitivity limits. Breakthrough Listen observations targeted Oumuamua during its outbound passage. The campaign used the L-band receiver and searched for both continuous and pulsed emissions. Data were processed with pipelines developed for technosignature searches. The analysis found no evidence of artificial radio emission. The null result was published as an upper limit. The visitor departed. The data remained. Inference from limited data remains constrained by geometry and timing. Oumuamua was observed for only weeks and at increasing distance. Lack of coma did not rule out outgassing of species difficult to detect. Shape estimates depended on assumptions about albedo and rotation. Uncertainties allowed multiple natural models to remain viable. Rapid follow-up changes the quality of inference for interstellar visitors. Early spectroscopy and imaging constrained composition and activity. Coordinated observations across facilities improve coverage. The preparation for future interstellar objects builds on the experience with Oumuamua. By early 2018, Oumuamua had faded beyond detection by large telescopes. No radio signals had been found, and no artificial nature had been established. The object remained a natural interstellar body with unusual but not unprecedented properties. Its passage demonstrated the value of wide-field surveys and rapid response. The brief visit added a new class of target for future SETI observations. Chapter 14: Tabby's Star. An unusual pattern of brightness dips was identified in data from the Kepler Space Telescope. The star, designated KIC 8462852, showed decreases far deeper than typical planetary transits. Some dips reached approximately 22%, and they appeared irregular in timing and shape. The pattern did not match known stellar variability. The anomaly attracted attention from both researchers and the public. The Kepler mission had monitored the star from 2009 to 2013 as part of its primary field. Data were made available to the public, and volunteers in the Planet Hunters project examined light curves. Irregular dips were flagged by citizen scientists. Professional astronomers confirmed the features in the calibrated data. The discovery was reported in 2015. Clouds passing in front of the sun produce temporary dimming. The depth depends on thickness and coverage. Shapes are irregular, and intervals between passages vary. The light returns to previous levels after each passage. The pattern reflects the structure of the intervening material. The clouds corresponded to whatever occulted KIC 8462852. Dips showed asymmetric profiles and variable depths. Durations ranged from hours to days. No periodicity was evident in the early data. The behavior suggested clumpy material rather than solid bodies. The star became known informally as Tabby's star after astronomer Tabitha Boyajian. The deepest events removed approximately 22% of the light. Smaller dips of a few percent occurred more frequently. The overall light curve remained stable between events. The combination of depth and aperiodicity was unprecedented in Kepler data. In 2015, Boyajian reviewed the light curve on a screen in her office. She plotted flux against time and noted the irregular drops. Colleagues gathered to examine the data and to rule out instrumental artifacts. The team checked for nearby contaminants and for data processing errors. The features persisted in multiple reductions. Tabitha Boyajian and collaborators prepared a paper describing the observations. They listed possible natural explanations, including cometary fragments and circumstellar dust. They also noted the unusual nature of the dips. The publication invited further monitoring. The hypothesis of alien megastructures was raised in public discussion, though not as the favored explanation in the scientific paper. That idea proposed large artificial structures, partially occulting the star. The suggestion attracted media interest because of its novelty. Researchers emphasized that natural causes should be examined first. The hypothesis served as a placeholder for unknown mechanisms. A scaffold erected around a building alters its silhouette from a distance. The structure is incomplete, and gaps allow light through in irregular patterns. From afar, the outline appears complex and variable. The scaffold itself is not the building. It is a temporary framework. The appearance depends on viewing angle. The scaffold corresponded to the megastructure speculation applied to Tabby's star. That concept imagined large collectors or habitats in orbit. Irregular dips were interpreted by some as evidence of incomplete coverage. The analogy captured public imagination, but lacked supporting data. Such structures remained hypothetical. Subsequent observations with ground-based telescopes and space observatories monitored the star during new dips. Multi-wavelength photometry showed greater dimming at blue wavelengths than at red. The color dependence indicated dust rather than opaque objects. Long-term monitoring revealed a gradual secular dimming in addition to short dips. The data supported models involving circumstellar dust clouds. Media coverage amplifies speculation when anomalies are presented without context. Headlines emphasizing alien structures attracted attention beyond the scientific discussion. The amplification increased public interest, but also distorted the balance of evidence. The episode illustrated the challenge of communicating uncertainty. Data from Kepler documented the initial dips in KIC 8462-852. The deepest event reached approximately 22% in 2013. The star was identified by Planet Hunters volunteers in 2015. Follow-up campaigns began immediately after publication. The designation Tabby's star entered common usage. Breakthrough Listen observed KIC 8462-852 with the Green Bank telescope in 2015 and 2016. The search covered a wide range of frequencies for narrowband signals. The observations were conducted during both quiescent periods and during optical dips. No technosignatures were detected above the established thresholds. The results were published as part of the broader survey. Dips continued. Signals did not. Follow up remains essential for anomalies of this kind. Natural explanations often require multi wavelength data collected over time. The dust model for Tabby's star gained support through color measurements and infrared limits. That process demonstrated how initial mystery yields to systematic observation. The case reinforced the principle of seeking natural causes first. Unusual light curves alone do not indicate technology. Stellar variability, circumstellar material, and instrumental effects can produce complex patterns. Distinguishing among causes requires additional evidence. The absence of corroborating signals leaves natural explanations as the default. By 2018, monitoring of KIC 8462852 had established dust as the leading explanation for its dips. No radio or optical technosignatures had been found. The star remained an object of astrophysical interest rather than a SETI target. Its light curve served as a reminder that the sky produces irregular occultations naturally. The quiet that followed the initial excitement became part of the broader record of non-detections. Chapter 15: The Great Silence as Data. Across decades of radio and optical searches, the pattern remained consistent. Telescopes pointed at nearby stars, at galactic centers, and at transient sources. Observations covered frequencies from hundreds of megahertz to tens of gigahertz. Data were recorded, processed, and archived. No confirmed extraterrestrial technosignature emerged from the collective effort. The cumulative result is a set of upper limits rather than detections. Each survey contributed constraints on the prevalence of transmitters above a given power. The limits vary with distance, frequency, and duty cycle. Together they define regions of parameter space that have been examined. The ensemble constitutes a measurement of absence. Weight accumulates when material is added incrementally. Each addition is small, and the total increases without sudden change. A scale registers the sum rather than the individual pieces. Measurement becomes meaningful only after many additions. The process is quiet and cumulative. The weight corresponded to the great silence recorded by SETI programs. Each null observation added a small increment to the total. That sum represented hours of telescope time and numbers of stars examined. Value was not zero effort, it was a measured quantity. The silence therefore carried weight as data. Searches conducted since 1960 have accumulated thousands of hours of observations. Targeted programs examined millions of stars across the Milky Way. Wide-field surveys added coverage of the galactic plane and extragalactic fields. Frequencies spanned the microwave window and extended into optical bands. The breadth of effort provided a foundation for statistical inference. In an archive room, researchers compiled logs from Ozma Phoenix, the Allen Telescope Array, and Breakthrough Listen. They entered dates, coordinates, frequencies, and sensitivity estimates into a database. Entries spanned paper notebooks and digital files. Compilation required standardization of units and formats. The work proceeded methodically over months. Archivists cross-referenced observations to avoid double counting. They calculated total time on sky and effective number of stars surveyed. Uncertainties were recorded alongside nominal values. The resulting catalog provided a basis for upper limit calculations. Each null result constrains the fraction of stars hosting detectable transmitters. The constraint depends on assumed transmitter power, bandwidth, and duty cycle. For powerful, continuously emitting beacons, the limits approach 1 in many thousands of stars. For weaker or intermittent sources, the limits remain less restrictive. The ensemble of constraints narrows the plausible range. Circles drawn on a map expand outward from a central point. Each new circle encompasses more area than the previous. Overlap between circles indicates repeated coverage. Gaps remain where no circle has reached. The pattern visualizes exploration. The circles corresponded to the parameter space examined by SETI. Frequency formed one axis, sensitivity another, and sky coverage a third. Each survey expanded the volume incrementally. Overlaps occurred where multiple programs observed the same targets. The expanding volume represented the limits achieved. The data suggest three broad possibilities consistent with the silence. Technological life may be rare, arising infrequently across the galaxy. Alternatively, it may be short-lived, with detectable phases lasting less than the time between surveys. A third possibility is that transmissions occur in forms or directions not covered by current searches. The measurements do not select among these, they constrain their relative likelihood. Null results accumulate meaning through repetition. A single non-detection provides limited information, but many provide a distribution. The accumulation allows statements about prevalence rather than about individual cases. The shift from anecdote to statistics follows naturally. By the 2020s, the combined archive included tens of thousands of hours of radio observations. Millions of nearby stars had been observed at least once, and thousands had been observed repeatedly. Optical searches added complementary coverage. The total effort spanned more than 6 decades. The scale allowed quantitative statements about the Great Silence. The Fermi Paradox, formulated in the mid-20th century, asked where extraterrestrial civilizations are given the age of the galaxy. Accumulated null results provide the primary empirical input to that question. The paradox is no longer purely theoretical, it is informed by measurement. Data do not resolve the paradox, they define its boundaries. Discussion now references upper limits rather than speculation alone. Silence accumulated, meaning followed. The question shifts from where are they to what do the limits imply. The shift reflects the maturation of the field from search to measurement. It invites models that accommodate rarity, brevity, or different transmission strategies. It also encourages expansion of search modalities beyond traditional radio. The reformulation keeps the inquiry grounded in data. Measurement differs from absence of effort. A measured silence carries information about the prevalence of signals above a threshold. The distinction is important for interpreting the Fermi paradox. The Great Silence is therefore a data set rather than a mystery alone. The Great Silence, as recorded across decades, stands as the central empirical fact of SETI. It does not prove that technological life is absent. It constrains how common or long-lived detectable phases may be. Weight of the null results increases with each survey. Expanding circles of parameter space define what has been examined. The silence remains, and it continues to be measured. Chapter 16: Hypotheses for the Silence. Hypotheses for the silence fall into several broad categories. Some propose that technological life is rare, others that it is short-lived. Additional proposals suggest that civilizations use communication methods not covered by current searches. A further group posits deliberate avoidance of transmission. The taxonomy provides a framework for interpreting null results. The leading explanations include the rare Earth hypothesis, the Great Filter, and models emphasizing brief technological phases. Each addresses a different stage in the progression from planet formation to detectable signals. Proposals are not mutually exclusive, and combinations are possible. Data accumulated to date do not favor a single explanation. The set of hypotheses therefore remains open. Paths branching from a common origin diverge over distance. Each branch represents a choice of direction. Some paths remain broad, others narrow quickly. Travelers select routes based on terrain and destination. The pattern of branching reflects underlying constraints. The paths corresponded to hypotheses explaining the Great Silence. One path emphasizes scarcity at the origin, as in rare earth. Another path emphasizes truncation after emergence, as in short lifetimes. A third path emphasizes divergence in communication methods, as in non-radio technosignatures. The branching illustrates how different assumptions lead to the same observed quiet. The rare Earth hypothesis proposes that conditions suitable for complex life are uncommon. Arguments cite requirements for plate tectonics, a large moon, and long-term climate stability. The hypothesis predicts a low occurrence rate for technological civilizations. That prediction is compatible with the absence of detections in nearby star systems. The hypothesis remains testable through exoplanet characterization. In a seminar room, researchers listed hypotheses on a whiteboard. They wrote rare Earth, great filter, short lifetimes, and alternative communication modes. Each entry included a brief description and a reference to supporting literature. The group debated the plausibility of each scenario. The board filled gradually with connecting lines. Researchers grouped the hypotheses by the stage at which they act. Some operated before the emergence of life, others after the development of technology. The categorization clarified which observations could test each idea. The resulting taxonomy guided discussion of future searches. The Great Filter proposes a bottleneck that prevents most life from becoming detectable. The filter could lie in the past, such as the origin of life, or in the future, such as self-destruction. If the filter is ahead, the silence reflects a short average lifetime for technological phases. If the filter is behind, the silence reflects rarity of emergence. The hypothesis frames the search as a probe of survival probabilities. A gate narrows a passage to a small opening. Many approach and few pass through. The structure does not destroy, it selects. Its width determines the fraction that continues. The gate functions as a filter rather than a barrier. The gate corresponded to the great filter concept. Narrowing represented a low probability transition between stages. Passage from simple life to technology, or from technology to long-term survival, served as candidate locations. The filter explained the silence without invoking deliberate concealment. That metaphor emphasized selection rather than absence. Short lifetimes propose that technological civilizations persist for centuries rather than millennia. Such brevity reduces the chance of temporal overlap with our searches. The hypothesis is consistent with historical patterns of rapid change and risk. Its prediction implies that most signals have ceased before we began listening. The scenario remains compatible with the observed upper limits. Hypotheses guide search design by identifying observable consequences. A rare Earth scenario encourages surveys of planetary habitability. A short lifetime scenario encourages searches for brief transients and artifacts. A non-radio scenario encourages expansion into optical and infrared technosignatures. Other proposals include deliberate silence, sometimes called the zoo hypothesis, and the use of communication methods beyond electromagnetic radiation. The zoo hypothesis suggests that advanced civilizations avoid transmission to allow natural development. The non-radio proposal suggests reliance on directed lasers, neutrinos, or other carriers. Both scenarios predict a quiet radio sky despite the presence of technology. The predictions are testable through expanded search modalities. Current data do not yet select among these hypotheses. Upper limits from radio surveys constrain powerful beacons, but leave weaker or intermittent sources largely unexplored. Optical searches have examined only a fraction of nearby stars. The parameter space remains large. The silence is therefore compatible with multiple explanations. The silence persists. Hypotheses remain. Each hypothesis explains the silence without invoking conspiracy or coordinated concealment. Rare Earth appeals to astrophysical and planetary constraints. The Great Filter appeals to probabilistic bottlenecks. Short lifetimes appeal to historical precedent. Non-radio and deliberate silence appeal to technological choices. Testability distinguishes useful hypotheses from speculation. A hypothesis that predicts specific distributions of planets, lifetimes, or signal types can be confronted with data. The task is to design observations that discriminate among scenarios. The accumulation of null results gradually narrows the set of viable explanations. The taxonomy of hypotheses frames the Great Silence as a problem with multiple plausible solutions. Data to date are consistent with rarity, brevity, and divergence in communication. The challenge is to expand searches to test each branch of the taxonomy. Branching paths converge on the same observed quiet, but they diverge in predicted signatures. Work ahead involves measuring which path the universe has taken. Chapter 17: What the Silence Means. Interpretation of the silence begins with what has been measured. Decades of observations have produced upper limits rather than detections. Those limits apply to specific frequencies, sensitivities, and sky coverage. Absence of signals does not constitute proof of absence. Data provide constraints rather than conclusions. The absence of detections does not prove that we are alone. It indicates that detectable civilizations are not common within the volumes and sensitivities examined. Such a result is consistent with rarity, with brevity, or with different communication practices. Distinction among these possibilities remains unresolved. Measurement narrows the range of plausible scenarios. A field without visible structures extends to the horizon. The ground is even, and no movement disturbs the surface. The emptiness is not a lack of ground, it is a lack of occupants. Observers can measure the extent and note the absence of features. The field provides a baseline for future comparison. The field corresponded to the radio sky as surveyed to date. Searches have covered many directions and found no persistent artificial sources. The emptiness reflects the current state of knowledge rather than a permanent condition. The measurement establishes a reference level. Future detections would stand out against this background. Measurements constrain two primary parameters, density and longevity. Density refers to the number of civilizations per unit volume. Longevity refers to the duration of detectable emission. The product of these determines the expected number of signals in a given survey. The observed upper limits imply that the product is low. In the archive, a researcher reviewed decades of observation logs. Files listed dates, targets, frequencies, and sensitivities. The researcher noted the steady accumulation of hours without detection. Patterns appeared consistent across programs. The record formed a coherent data set. A researcher considered what the absence implied for future planning. Data suggested focusing on broader frequency coverage and longer integrations. Absence also suggested expanding searches beyond traditional radio. That reflection guided the next proposal. The data suggests that if others exist, they are either rare, quiet, or using methods we do not monitor. Rarity reduces the probability of a nearby source. Quietness reduces detectability even if sources are numerous. Different methods place signals outside current search bands. The combination of factors remains compatible with the observed limits. Tuning an instrument requires adjusting until a reference tone matches a standard. The process involves small increments and repeated listening. The goal is not to create sound, but to align with an external reference. Calibration establishes a known baseline. The procedure is methodical rather than dramatic. The tuning corresponded to the calibration provided by the Great Silence. The null results set a reference level for the prevalence of detectable civilizations. Future surveys can measure deviations from this baseline. The calibration does not predict detections, it defines sensitivity. The process allows interpretation of future data in context. The implication is not despair, but calibration. A universe without frequent loud neighbors allows clearer interpretation of our own development. The silence provides a boundary condition for models of technological longevity. It suggests that detectability is not guaranteed by existence alone. The insight redirects effort toward understanding longevity and detectability. Limits inform responsibility by clarifying our apparent isolation. If detectable civilizations are rare or short lived, the preservation of our own capability gains importance. The data do not dictate ethics, they provide context. The context encourages careful stewardship of technology and planetary systems. Density of technological civilizations appears low based on current surveys. Longevity of detectable phases appears limited to less than the timescales probed. Methods of communication, if present, appear not to include powerful isotropic radio beacons in our surveyed bands. The three parameters together explain the observed quiet. The constraints will tighten as surveys expand. The sky, as examined, does not appear crowded with loud neighbors. Nearby sun-like stars show no evidence of continuous high-power transmissions. Galactic plane surveys, repeated over years, remain quiet at the sensitivities achieved. Extragalactic searches add further limits. The overall picture is one of sparsity rather than abundance. Quiet persists. Calibration continues. The silence serves as a boundary condition for future searches and for thinking about our own longevity. It defines the starting point for models of prevalence. Such a boundary informs the design of instruments and the selection of targets. It also frames discussions of risk and sustainability. The boundary is empirical rather than theoretical. Expectations adjust in light of measured limits. A universe with few detectable civilizations encourages searches for subtle or intermittent signals. It also encourages study of our own detectability. The adjustment is pragmatic rather than pessimistic. Calibration of our place in the cosmos proceeds through accumulated null results. The silence does not close the question, it refines it. Density, longevity, and methods remain the key variables. Future observations will test whether the quiet persists at greater sensitivity. The meaning of the silence lies in its role as a measured baseline for what follows. Chapter 18, Listening Forward. Future searches will expand in sensitivity, bandwidth, and sky coverage. Plans include observations with next-generation radio arrays and with optical facilities. Goals include examining larger volumes of parameter space than previously possible. The approach builds on lessons from decades of null results. Expansion will be incremental rather than revolutionary. The Square Kilometre Array, under construction in Australia and South Africa, will provide unprecedented collecting area. The next generation Very Large Array, proposed for North America, will offer high sensitivity at higher frequencies. Both facilities will allocate time for technosignature searches. The combination will improve coverage across the microwave window. The capabilities will support both targeted and wide-field surveys. A horizon widens as an observer gains elevation. More distant features become visible, and the area encompassed increases. Expansion does not create new land. It reveals what was already present. The process is gradual and cumulative. A wider view allows better mapping. The horizon corresponded to the future reach of upcoming telescopes. Increased sensitivity will allow detection of fainter signals at greater distances. Wider bandwidth will enable simultaneous coverage of many frequencies. Larger fields of view will increase the number of stars observed per pointing. The widening will expand the parameter space examined. Sensitivity improvements of an order of magnitude are anticipated with the SKA. Bandwidths of several gigahertz will be processed in real time. Sky coverage will approach continuous monitoring of accessible declinations. Data rates will reach petabytes per day, requiring automated pipelines. The technical advances will translate directly into deeper upper limits or potential detections. In a control room, a team prepared the observing plan for the next survey. They selected target lists based on exoplanet catalogs and stellar proximity. They scheduled calibration observations to precede science pointings. Software pipelines were tested with simulated signals. The checklist was reviewed before the first night. Engineers verified receiver tuning across the planned frequency range. Astronomers confirmed that data storage capacity matched expected volumes. The team conducted a dry run to validate end-to-end flow. Preparations concluded with a readiness review. Machine learning will improve detection of faint and complex signals. Algorithms trained on known interference can distinguish terrestrial sources from candidates. Models can search for patterns not anticipated by traditional matched filters. The methods will reduce false positives while maintaining sensitivity. The integration of machine learning into pipelines is already underway. A watch kept through the night involves steady attention rather than constant action. The observer remains present, and instruments record continuously. Periods of quiet are expected and do not end the watch. The value lies in persistence rather than in immediate results. The practice embodies patience. The watch corresponded to the continued effort to listen for techno signatures. Telescopes will operate night after night, accumulating data. Absence of signals to date does not terminate the program. Practice continues because the parameter space remains incompletely explored. The commitment reflects scientific humility. Optical and infrared searches will complement radio efforts. Programs will look for pulsed lasers, for megastructure transits, and for waste heat signatures. Expansion beyond radio diversifies the types of technosignatures considered. The approach acknowledges that technology may manifest in multiple spectral domains. Combined coverage improves the chance of detection if signals exist. Humility sustains the search by accepting uncertainty. Continued listening does not require certainty of success. The practice values measurement over assumption. The attitude supports long-term programs. The next generation facilities, including the SKA and the NGVLA, will provide the foundation for this expansion. Machine learning will process the resulting data streams in near real time. International collaborations will share data and coordinate follow-up. The infrastructure will support both SETI and broader astrophysics. The synergy increases scientific return. The silence to date informs strategy but does not end in query. Upper limits guide the selection of frequencies and sensitivities for future surveys. Absence of detections motivates broader searches rather than cessation. Data suggest where not to look with the same methods and where to expand. The process is iterative. Listening continues. Data accumulate. The Fermi Paradox remains open, but it is now framed by data rather than by speculation alone. Accumulated null results define the current boundaries of the discussion. The paradox invites continued observation rather than premature conclusion. Such a framework allows testable predictions about density and longevity. The question persists, now with quantitative context. Continued listening reflects a commitment to empirical inquiry. The act does not depend on immediate success. Value lies in the accumulation of knowledge about the sky. Practice continues regardless of outcome. Work ahead involves building instruments, refining algorithms, and conducting systematic surveys. Effort will expand the horizons described earlier and maintain the watch described earlier. The silence to date will serve as calibration for future measurements. Fermi Paradox will remain a guiding question, now anchored in data. Listening forward continues as a measured, patient endeavor.